All right, welcome back, Earth scientists. This is the first unit of Earth Science B. Let me get my presentation going here. Unit 6, plate tectonics. And we did skip over Unit 5, so don't think you're going crazy. We skipped Unit 5. We're starting with Unit 6. The only reason we did that is because we are still following the curriculum laid out in the textbooks that we use in the in-person classes. And Unit 5 is another unit on space. Just for the sake of time, we're jumping forward to talk about plate tectonics for this unit. So Unit 6, plate tectonics, 4 lessons, so it is a little bit of a longer one, but I think it's really interesting. Hopefully you will too. These are the 4 questions, our essential questions that hopefully you'll be able to answer at the end of this unit. How do we know the structure of Earth's interior? So what's inside the planet? What evidence supports the claim that Earth's surface is made up of slabs of rock that are moving relative to each other? What's the evidence for plate tectonics, essentially? How does the flow of energy from Earth's interior affect its surface? And how do plate motions affect people? So we're going to go over some of the highlights. For that, of course, I'm not personally going to answer all of those questions. I'll touch on most of them, but remember that you do have to watch all the videos in the guided notes and do all of the assignments in your guided notes as well to be able to answer these 4 questions fully. Okay, so first, let's think about what's inside the Earth. Before we even go into the plate tectonics thing, we have to know what's beneath the surface of Earth. And the way we've gone about figuring that out, we've used 2 different strategies, right? Our first one is a little more obvious, using direct evidence from rock samples. We drill down as deep as we possibly can into the crust to try to figure out what it's made of, what might be below the crust. This is awesome, and we've gotten a ton of good information from this strategy, but know that we have never drilled all the way through the crust into the mantle, right? So we've only gotten crust samples, which is super useful, but doesn't tell us a whole lot about what's beneath. We still have to kind of make some jumps and some inferences to hypothesize what might be beneath the crust. But we've also gained some evidence, indirect evidence from seismic waves. So seismic waves are what occur from an earthquake. When an earthquake occurs, you get this sudden movement in tectonic plates, and we'll talk about that later on, but there's this sudden movement that sends shock waves throughout the Earth, not just the crust, but also through the center of the Earth. And those waves travel differently depending on what they're moving through. So, for instance, some of those waves don't really travel through liquids. So we can use evidence from these waves to infer that some of the layers beneath the Earth are in fact liquid. They're not solid at all. So we've gathered both direct and indirect evidence to figure out what is happening below the crust. Okay, and using that evidence, we've deduced that there are 3 main layers to the Earth, and we can denote the layers of the Earth differently depending on what we're looking at, whether we're looking at composition or structure, all of those things. So we'll talk about that a little bit later. But first, sorry. All right, my dog likes to interrupt sometimes. Sorry about that. Okay, so we've got 3 major layers that the Earth can be separated out into initially, and that is the lithosphere, the mantle, and the core. So the lithosphere is solid, the mantle is semi-solid, right? So it's solid, but it flows a little. And then the core is a combination of liquid and solid. But we're going just out of composition, right? So the crust is made out of lighter materials, mantle, slightly heavier materials, and then the core is super heavy, dense materials. So here, there are 2 ways we can denote the layers in Earth's crust. And you can see one way broken out on the left side here, and the other way broken out on the right side. So on the left side is kind of what I already went through with you on the previous slide, right? You've got your crust, a mixture of granitic and basaltic rocks, all extremely solid. Mantle, you've got your silicate materials, and the core is heavy iron and nickel. right? So that's just breaking out the Earth into the layers of what it's made out of, okay? On the right side, which is actually what we will tend to use more in this unit, is breaking out layers into how they act. So not necessarily what they're made out of, but their state, whether or not they flow, and how they respond to different stimuli. Okay, so up at the top, what we call the crust is the lithosphere here. And the lithosphere is extremely rigid. So it will not bend, it'll break, right? Solid and rigid. And then the asthenosphere is kind of the last piece of pretty rigid, maybe a little more flowing crust. Okay, it's technically part of the mantle, but it acts more like crust. Okay, and your mesosphere is where you get that really flowing kind of plastic-like, kind of like silly putty sort of texture. So this is what your lithosphere is really flowing on top of. That's what your plates are moving on top of, is that mesosphere. Okay, your outer core is completely liquid, still made out of iron and nickel, but totally liquid. And the inner core, super solid and dense. Okay, so there, again, your right side, the layers of the Earth based on their function, and the left side layers of the Earth based on what they're made out of. All right, so the crust or the lithosphere, we can kind of use those interchangeably. Again, solid outer layer of the Earth, both dry land and ocean floor, right? So the ocean floor is part of the lithosphere, so don't forget that. Oceanic crust is mostly made out of basalt, which has a lot of iron in it. It's that darker color rock, whereas continental crust is mostly made out of silicates or granite. So that tends to be lighter and less dense. So granite is lighter in color, even if your granite countertops are black, right? When we're talking geology, granite is lighter in color, kind of pink or white, with maybe some black flecks in it. So continental crust is largely lighter and less dense. Oceanic crust is denser and heavier. Okay, and our mantle. So divided into, I wouldn't actually call the lithosphere part of the mantle, but we can classify the asthenosphere and the mesosphere as part of the mantle. Solid, really hot, but this is where you get that silly putty texture. And our core, remember, divided into two different layers, the outer core and the inner core. The outer core is liquid and the inner core is solid. So the outer core is the only layer of the Earth that is actually liquid. The mantle is silly putty. Okay, so to talk about plate tectonics and plate motion, we have to remember how energy is transferred. So we're going back to Earth Science A, what we talked about at the very beginning of Unit 2. So just a little bit of a memory refresh. You can transfer energy in 3 different ways: radiation, waves, conduction is touching, and convection, remember, is when you get that differences in densities. So you get movement of matter, right? Warmer things rise, cooler things sink. And that's that convection piece that's going to become very important when we talk about plate tectonics. Okay, so convection. Here we've got convection currents, and this is what drives plate motion, is convection currents within the mantle, within the asthenosphere. Okay, so convection currents happen when you get warmer crust that's on the border of that outer core there. Here, it gets really hot and it rises toward the surface. And cooler mantle up here will sink down toward the outer core. So you get this overturning just like boiling water, except much, 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 much slower, right? It's that same overturning, and we call this a convection current. This mantle is flowing over time. Remember, the mantle is still classified as being a solid, but it's plastic-like. It's that silly putty, slow motion bending over time. And that kind of acts like a conveyor belt on the surface, pulling these lithospheric plates and causing them to move. Right? So convection is really the driver behind plate tectonics. All right, so we're going to do a brief history of plate tectonics and where it came from. Alfred Wegener is kind of the person, the person behind the theory of continental drift. So continental drift was the theory that was hypothesized before plate tectonics. Okay, so it's the precursor. So they're not interchangeable terms. Definitely we want to talk about plate tectonics when we're talking about the current theory of plate motion. And continental drift was something that Wegener proposed, which was super awesome. He was the one that noticed that the outline of the continents kind of line up like puzzle pieces, and like they maybe might have been one whole landmass, which in fact they were. And he's the one that gave it the name Pangea. And he hypothesized that those continents must have drifted over the oceans, floated on the oceans away from each other. And he named that theory continental drift. So these were the pieces of evidence that he gathered to support his theory of continental drift, right? So land features such as mountain ranges, they lined up on separate continents. If you put them back together, you could see that they lined up. He also found some fossils. He would find fossils of certain organisms on one continent and fossils of the exact same organism on the other continent, and there's no way that they could have crossed the oceans to live in two separate places. So at one point in time, those two continents must have been joined for those organisms to be able to be found in both of those places. He also found evidence from climate changes that showed that glaciers existed in places that are much too warm for glaciers to exist today, meaning that those land masses must have moved in order to have had glacial activity. So those were the main pieces of evidence that Wegener had to support his theory of continental drift. And most of these pieces of evidence are true, right? Those continents were moving. The real issue is they weren't floating on the oceans, right? They weren't drifting and floating on water. In fact, the oceans were moving with them. The entire plate, the surface of the earth, was moving. And that's where his continental drift theory broke down. So then Harry Hess came in and kind of edited Wegener's theories a little bit, since Wegener couldn't explain why the continents were moving, really, other than floating on the oceans. Hess was the one that came up with the idea for seafloor spreading. He explained what seafloor spreading was. And seafloor spreading shows us that plate movement, the mechanism behind the plate movement. All right, seafloor spreading happens when two plates are moving away from each other. So it happens at divergent plate boundaries, which eventually form oceans. So you get this ridge in the middle of oceans that is constantly creating new crust, causing oceans to become larger and for continents to spread apart. Okay, so this was Hess's contribution to the theory of continental drift, and this is really when we start calling it plate tectonics instead of continental drift. All right, so let's see Hess's evidence for seafloor spreading. This is what he found to support his theory for convection currents and seafloor spreading. So he found molten material, pillow-shaped rocks formed when molten material erupts and hardens quickly. So he observed that happening. He also found magnetic stripes. So what happens is when lava cools, it records the orientation of Earth's magnetic field. And every few thousand years, that magnetic field switches. So you can see these stripes that happen when the field is oriented one way, and we're forming rocks that way, boop, doop, doop, and then that magnetic field switches, and at mid-ocean ridges, now the new orientation is being recorded. So it starts to form these stripes outward that are recorded at mid-ocean ridges. And you'll see a video about that. You'll see some more figures that explain that a little better, because it can be kind of confusing, but this is a really important piece of evidence for plate tectonics. Hess also conducted some drilling samples to deduce the age, and he found out that rocks that are closer to the ridge, closer to the place where the plates are spreading apart, are younger, right? And rocks that are farther away from that plate boundary are older. So new rocks are being created at that mid-ocean ridge. So these are three really strong pieces of evidence that Hess came up with to support seafloor spreading and plate tectonics. Okay, so here, this is not a mid-ocean ridge, right? This is actually two plates colliding. So this is a convergent plate boundary. So this is showing your mid-ocean ridge would be over here, somewhere spreading apart, and now two plates are coming together here. And what happens when this occurs, ocean plates are more dense. They're made out of denser material, remember, iron and basalt. So they will always sink beneath continental plates in what we call a subduction zone. So you get subduction happening at continental and oceanic plate boundaries. This oceanic plate gets pushed underneath this overriding continental plate, and as this gets pushed into the mantle, it starts to melt. And there's lots of water contained in this oceanic plate, right? Those sediments are saturated. And that water decreases the melting point, so it allows it to melt much faster than normal crust. And that melted oceanic crust then rises up and you get volcanoes. So at a convergent plate boundary, you get one oceanic plate subducting, creating volcanoes. So things like the Cascade Mountains in the Pacific Northwest of the United States are formed at a plate boundary like this. This is why those volcanoes like Mount St. Helens are located there. That's a convergent plate boundary. So our final theory of plate tectonics, right? This is what the plate tectonic theory is. You have tectonic plates that are floating on top of the asthenosphere, right? So including oceanic crust. Convection currents rise in the asthenosphere, right? Warm material rises and spread out underneath the lithosphere. Those convection currents cause plates to move, causing changes in Earth's surface. And those changes include volcanoes, mountain ranges, ocean trenches, earthquakes, all of those type of things result in plate tectonic action. And plate boundaries, which I've kind of already hinted at a little bit, right? Those are the edges of plates. Those are where different plates meet. And there's 7 major plates, but lots of little plates scattered around Earth. So there's lots of different plate interactions happening all over Earth. And those rocks move past each other in different ways. Right, so at a transform boundary, this is where two plates are sliding past each other. Let's see if I can so they're not moving into each other and they're not moving away from each other. They're just kind of going past each other. So this is where you get major earthquakes, right? The San Andreas Fault is at a transform boundary. A divergent boundary, so this is where plates are moving away from each other. This is where we get seafloor spreading. This is where we get mid-ocean ridges, right? So you either, if it's on land, you'll get a rift valley. So the Great African Rift Valley is a divergent plate boundary, and eventually that will fill in and you will become a sea and an ocean eventually. Not in our lifetimes. It'll take millions of years, but eventually that will happen. And the mid-ocean ridge runs right down the middle of the Atlantic Ocean. This is happening. So you get constant upwelling of new lava, creating new crust and pushing those continents farther and farther away from each other. And last but not least, a convergent plate boundary is where two plates are coming together. So again, when we talked about one continental plate and one oceanic plate coming together, that oceanic plate will subduct underneath the continental plate. With two oceanic plates, one will be forced down to subduct between the other one, but it'll kind of pull the other one down with it. So you get these really deep trenches forming at ocean-ocean convergence. When you get continental-continental convergence, those two continental plates won't subduct. They don't want to subduct. They're too light to go underneath each other. So they actually end up pushing each other upward. So you get lots of mountain building happening. And that's what's forming the Himalayas right now, is the Indian plate is crashing into that Asian plate and pushing those two continental pieces upward into big, tall, jagged mountains. Right? So at convergent plate boundaries, you can get volcanoes, you can get earthquakes, you can get really, really tall mountains, right? There's lots of interesting, crazy stuff that happens at convergent plate boundaries. So in your guided notes, we're going to go into several different famous volcanic eruptions, right? We'll talk about Mount St. Helens, some other historical, really large volcanic eruptions. I'm going to let you do that exploration on your own. I'm not going to go over them with you here, but know that they are linked back to these plate tectonic movements over time. All right, that's all I have to say to you here about Unit 6. Dive into your guided notes and have a great day. I'll see you later.